So I confess that when I first learned induction in university, I was blown away. I understood up to a point what was going on. I mean, certainly when my professor talked about a base case, P of 0, that made perfect sense to me. And then I understood what exactly he was proving when he started talking about this, the induction step. But then somehow from these two things combined, he managed to prove that for all n some predicate held. This was like magic. I didn't understand what was going on. And I wasn't completely convinced either. I sort of accepted it on face and then moved on. I imagine that this is what a lot of you are doing as well right about now. And believe it or not, I actually want you to understand what's going on, and I want you to believe that induction is a valid proof technique. So this video is going to try to help convince you of that. Because even if you don't believe in induction, I'm going to show you something else that you probably all do believe in. So this is called the well-ordering principle. And I'll abbreviate it to WOP because I never want to write that again in this video. It says the following. Every non-empty subset of the natural numbers has a minimum element. If you think about this for a second, it should seem very obvious. Here are some examples. The set 1, 2, 3, its minimum element is, of course, 1. The set of primes, its minimum element is 2. The set of, say, powers of 3, starting at 3, 9, 27, its minimum element is 3. Even the natural numbers itself, it has a minimum element. Its minimum element is 0. So this is a statement which you should all accept to be true. Even if you've never actually thought about it before in your lives, certainly it seems very obvious that this should be true. And now, the thing that I'm going to show you today is that if you believe deep down in your soul that the well-ordering principle is true, then you should also believe induction is true. That is, I'm going to prove the following. The well-ordering principle implies induction. If the well-ordering principle is true, then induction is also true. So let's get started. We're going to assume that the well-ordering principle holds, and we're going to assume that induction doesn't. And from this, we're going to get a contradiction. Now, what does it mean for induction not to hold? Well, it means that for some p of 0 is true, and for all k, p of k implies p of k plus 1, these things are true. But for all n, p of n is false. That is, induction didn't work on this predicate p. We proved the base case, we proved the induction step, but somehow we didn't manage to conclude that all natural numbers had this property p. Okay, so here's what we're going to do. Let A be the set of natural numbers n such that p of n is false. By assumption, A is non-empty. That is, we're assuming that for all n, p of n is false. Therefore, there has to be at least one particular n where p of n is false. Now, what can we conclude? Well, by the well-ordering principle, A is a non-empty subset, and therefore, A has a least element. and we're going to call it, say, R. So what do we know about R? R is in A, so P of R is false. Could R be 0, for example? No. And why not? P of 0 is true. We've assumed that right up here. So R is greater than 0. But then what do we know about P of R minus 1? It has to be true. And why is that? Because R minus 1 is less than R, and by definition, R is the least element for which P of n is false. But then P of R minus 1, well, that implies P of R. Why? Well, because of the quote-unquote induction step over here. So P of R is true. And we have our contradiction. And this concludes the proof. So in summary, if the well-ordering principle is true, then induction is also true. That is, if you believe in your heart of hearts that the well-ordering principle holds, that every subset, every non-empty subset of the natural numbers has a least element, then you also believe that induction is a valid proof strategy. And just as a side note for those of you interested, something even more is true. It turns out that induction implies the well-ordering principle. That is, if induction is true, then the well-ordering principle is also true. And therefore, these two statements are logically equivalent to each other. The proof of the converse is a little bit trickier, but certainly not out of your league. Okay, that's all for this video. Thanks for watching and have a great day.